Hey guys, I'm Bob with Math, and today I'm going to be showing you integration by parts. So essentially, integration by parts is the reverse product rule for integration. What we use it for is when we have a product of two functions and we want to find its integral. So in this case, we have x and sine of x. And you may want to try using u substitution. However, you'll realize that you can't really make a u substitution that'll work. You can set x equal to u, but then you just end up with the same exact integral, but in u. So we're going to use this cool formula, which we call the integration by parts formula. Where we have the integral of u with respect to v, and this is equal to uv minus the integral of v with respect to u. Now this looks very weird, very complicated. Why do we have u and v in the same, it doesn't make sense. U and v are both functions of x. So if you think about it, this is like u of x, and then we have like dv of x. And so if you have x, and then there's x everywhere. So if you see it like that, I guess, I don't like to see it like that, but that's something you could see it as. Everything has to do with x. But I will derive this after this problem. For now, it's easier to learn how to use it. And essentially speaking, what we have is this side of the equal, this side of the formula. We have u dv, right? I mean, it's a little tricky figuring out what to use for u and dv. If you recall, when you're doing u substitution, you may set u equal to let's say it was cosine of x, then you do du equals negative sine of x dx. So the differential of u is equal to negative sine of x times the differential of x. So you can kind of see it like that. We can attach this dx to either our sine of x or our x. Saying we have x dx times sine of x, or exactly how it's written there, x times sine of x dx. That should still sound complicated, but the point is that the dx can follow whichever function. Now, how do we determine which function it should follow, or shouldn't follow in this case? We use the Liate method. I don't know how to pronounce that. Now, professors teach different ways. I didn't learn with one, but this one is the most common one that I've seen, and it works good 90% of the time-ish. So whenever you're faced with an integral that you believe you should be using integration by parts, in order to find out where to attach our dx, you want to use the Liate method. So this takes priority of what not to assign it to. So if we have a logarithmic function, we don't assign it to that. Liate stands for logarithmic, inverse trig, algebraic, trig, exponential. Let's say in this case we have an algebraic function x and we have a trig function sine of x. We should attach the dx with the trig function, the one that appears last, not with the algebraic function. So what the Liate method does is it helps us pick our u here. Our algebraic will be our u here, x. And then what I'll choose for dv is sine of x, right? Sine of x dx. So this helps us figure out this portion right here, the u dv. We have the u and we have the dv. Now, what we can do is we can take the differential of u, that'll just be dx, and we can integrate, we can integrate both sides. If we just do the integral sign, the integral of dv is just v, okay, and then the integral of sine of x dx is negative cosine of x. Okay, so from here, now it's just about using the formula. We'll have uv, so u times v, negative x cosine of x, and then minus the integral of v du. Minus the integral of v du. So our v is negative cosine of x, negative cosine of x, and our du is just dx. So this is what we're left with. Now obviously you can combine these two and make a plus, which is exactly what I'll do. And then the integral of cosine of x is just sine of x. So we're going to end up with negative x cosine of x plus sine of x plus c. And this will be our integral. And if you try to differentiate this, you will end up getting this. But the point of this was to show you how we choose our u and our v and stuff like that. So the derivation of the formula starts off with the product rule for differentiation. If we take the derivative, so assuming u and v are functions of x, we take the derivative with respect to x of u and v, like u times v, we'll get u times the derivative of v plus v times the derivative of u. Now, what if we took what if we added what if we multiplied everything by the differential of x? So we'll have d dx of uv, and then dx, and then this equals u dv dx, dx plus v du dx dx. So we multiplied everything by the differential of x, and then we were to integrate every term. So integrate, integrate, integrate. So we're integrating every term with respect to x. Now, this isn't the proper, explanation for integration by parts. But what you can do is, well, here we have derivative and integral. You know that those just cancel out, right? So we're just set up with uv. On this side, we can cancel out the dx's, right? Like a fraction. U dv. And then same thing here, v du. Now, obviously, this does not, it's not, this isn't how differentials actually work. But for the sake of showing a derivation of this rule, at least at a basic level, we can use this. And then from here, we can just minus the integral of v du on both sides. And we'll end up with, on this side, we'll have u dv equals uv minus v du. And this is how we end up at our formula. What if we had something like x cubed times e to the 2x dx? If you tried to do integration by parts, I'll just show you what you'd end up getting really quick. I'll do it super fast. So this is du, and then dv and v. So our u, we have algebraic and exponential. Algebraic comes first, so we have our u is x cubed, du is 3x squared dx, dv is e to the 2x dx, don't forget the dx, and then v is, we integrate this, it's 1/2 e to the 2x, that's it. Okay, so, we end up uv x cubed times 1/2 e to the 2x, and then minus v du. So v is 1/2 e to the 2x, and then du is 3x squared, so I'm going to make this a 3. Then we can put like x squared here, dx. What do you notice about this integral right here? This integral is another integral they have to perform another integration by parts on. So then you have to separate this, and you're going to notice that this is going to continue on, I think, 3 times more, like apart from this one. So another 3 times. That gets really tedious. Now, this doesn't work for everything, but I know for stuff that has algebraic, for stuff that has a derivative that will end in 0, we can use something called the DI method or the tabular method. And essentially, this makes taking integrals for these certain integrals much easier. So I label it DI. This stands for derivative and integral. And then what you're going to do is you're going to put plus, minus, plus, minus, plus. It depends on, so like I have x cubed. Okay, I'll explain what this right now. Derivative and integral. Think about u and dv. What you would select for your u and your dv. Here, you would put where you select for your u, and here you put where you select for your dv. So your u is going to be x cubed, and your dv is going to be e to the 2x. Now from here, we just continue taking the derivative on the d side. So we'll get 3x squared, 6x, 6, and 0. And I just made it up until when the derivative equals 0. Obviously, you can continue doing it. It doesn't really matter. It'll be 0, 0, whatever. The point is, once you get to 0. Now, on the integral side, if you differentiated for the d side, on the I side, you should integrate. So we're going to get e to the 2x over 2, e to the 2x over 4, e to the 2x over 8, and then this last one's going to be e to the 2x over 16. I know it's a little messy, but I can work with it. And then what we're going to do is you're going to make little diagonal lines that point to the next one. So the first d will go to the second I. Second d, third I. Yeah, third one. Fourth one. Fifth one. Now, obviously, I didn't make any more because 0 doesn't point to anything. Like, whatever 0 points to is going to be multiplied by 0. Because we're going to multiply each of these. So we're going to have positive x cubed times e to the 2x over 2. So x cubed times e to the 2x over 2 minus 3x squared times e to the 2x over 4. So minus 3x squared e to the 2x over 4 plus 6x times e to the 2x over 8. That's going to be 3/4 again. Plus 3x e to the 2x over 4. And then minus 6 e to the 2x over 16. So that's minus 3/8. Minus 6 e to the 2x over 16. And then obviously your plus c. And then this is the integral. This is our answer. Which that made it a lot easier than using integration by parts over and over again. So here we have the integral of e to the x times sine of x dx. And, you know, this integral is a little tricky because we have to, like, you're going to see, we're going to be doing some integral algebra. That's what I like to call it. So let's use our normal principles, du, dv, v. So our u, we have trig and exponential. Trig comes before exponential, so we're going to have our u is sine of x, du is cosine of x dx. And then dv is going to be e to the x dx, and then v is e to the x. So we're going to end up with uv is e to the x sine of x minus v du e to the x cosine of x dx. And then we're going to have to do integration by parts once again. This time I am writing it out by hand. So I'll do minus, and then I'll start like a bracket. That's what I'll call it. So we're going to have u equals du equals dv equals v equals. So our u, we have trig and exponential. So our exponential is going to be cosine of x. Or, yeah, cosine of x. And then du is going to be negative sine of x dx. So dv is going to be e to the x dx, and v is e to the x. We just do similar thing, e to the x cosine of x minus the integral of negative sine of x dx is part of our du. So I'm going to put this negative in front here, and we have e to the x sine of x dx. Okay. Now I'm going to distribute the negative, so we're going to end up with e to the x sine of x minus e to the x cosine of x. So I can actually factor that. And then we're going to have minus e to the x sine of x dx. Now, what do you notice about this integral? It's this one. So if you think about it, think about this equals this, like an equation, like 3x equals 6x. We can, well, it's a really bad example, but like 3 plus 7x. And we can minus the 7x, just like we can do here. So essentially what I can write here is I can add this to both sides. I can add the entire integral to both sides. So we're going to end up, imagine I do it on the other side as well. We're going to end up with 2 e to the x sine of x dx is going to be equal to whatever this is. So this is e to the x sine of x minus cosine of x. Okay? And then I just divide by 2 to get our integral. So realistically, if I divide by 2, I don't even need this equal sign. I just say divided by 2. And this is like this is known as like the double integration by parts. And then, yeah. Now, actually, a really cool trick to remember this formula is ultraviolet voodoo. So whatever u dv equals ultraviolet voodoo, like v do du. Ultraviolet voodoo. That's just something I don't really know any other tricks for it, but that is a way to learn it. So here we have a very simple integral. This is kind of just like me showing you, the integral of ln of x, that's just going to be 1 over x plus c. You're wrong. That's not what it is. The derivative of ln of x is 1 over x. This is completely wrong. This is secretly an integration by parts question. So I'm going to write down my u, du, dv, and v, right? But what do we choose as our u? All we have is ln of x. We just have one function. We don't have two functions. Ish. We can see it as 1 times ln of x. And 1 is technically a function of x. Any constant is a function of something. So what I can do is we can use the Lie method. 1 is algebraic in this case. Ln is logarithmic. Logarithmic comes first. Logarithmic is our u. So ln of x is our u. Du is 1 over x dx. Our dv is going to be 1 dx, so just dx, which means our v is x. So we can write this as uv is x times ln of x minus v du. So we have v, which is x, times du, 1 over x dx. These cancel out, we're just left with dx, which is x. So we're going to end up with x ln of x minus x plus c. And that's the integral of ln.